and from the current slide. All right, now let's go over just a couple of issues. First, pretty important one, and I'm wanting this on Screencast-O-Matic, that's why I waited to announce it. All of you done the student course evaluations? Yes? Good. Yes? Not yet? Okay. You got time. Yes, yes? No? Yes? Okay. So, huh? Okay. One place you can do is if you check your email, I know there's an email was sent about it, maybe more than one.
I haven't received it, but
what's that?
I haven't received that email, but a teacher emailed me the link.
You what?
I haven't got that, but a teacher sent me the link.
Who sent you the link?
Mr. West.
Oh, he did. So that email hasn't been sent yet?
Yeah, I haven't gotten it yet.
Well, one of my other classes said they had sent
Some
it.
people got it, some people don't.
Really?
Yeah, I didn't get it.
That's pretty pathetic. Okay, if you haven't gotten the link elsewise, it's called Smart Evals. Okay, you can go to the Lawson State homepage. Okay, and you know at the top of the homepage is a bar with a bunch of blue tabs on it, directories, student suite, faculty suite, all those tabs at the top of that page. Over near the right-hand side, it seems like, there's a big gold tab that says Quick Links. So click on Quick Links. Okay, then you'll see a whole menu of things, and go down and start looking for, I believe it's either under surveys, student surveys. It's been a long time since I looked at it, and what you're looking for is Smart Evals. But I think it's usually listed under surveys or student surveys. And it's pretty much down because I think they do those alphabetically. And somewhere down the list you'll see surveys or student surveys or student course evaluations. There will be some sort of a thing like that with, when you click on it, you'll get Smart Eval. What's that? Okay, yeah. It sounds like the emails didn't go out evenly. I don't know why. Are you checking your Lawson State email or not your personal email? I don't know. This system is not very good. Well, look under Lawson State webpage, the tabs at the top, go all the way over to you see the gold one that says Quick Links. Click on Quick Links and scroll down until you find, I think it's surveys. It may be student surveys or, like I said, it's been a long time since I've looked at that to see. Most of the time they send an email with a link in it and you just go there.
For the student evaluation?
Yeah. Did you get
Yeah,
it?
I did. I completed mine.
Okay, how did you get access?
Just went to my email.
So you got an email.
I had it. It came out. It came out around when it was elected for the SBA officers.
Right.
Yeah, it came around.
Okay, is that what the title is on it? It's not evaluations, but
Yeah, it might say something about SBA.
yeah. Look for an email that's about SGA, Student Government Association.
Yeah. It should directly right to it.
That may be the issue. They put it under a title that you never would have expected. This would have been in the last 2 weeks, right?
Yes. Yeah, it say vote for SGA officers now.
Say that again.
It say vote for SGA officers now.
You found that?
Oh, yeah, I see it.
Okay, that's it. Wow. Who would have thought that's where they would have put the student course evaluation? Yeah. I do not understand this place sometimes. All right, good deal. So we see which ones of you are student government minded and which are not. Okay. All right, good deal. Any questions before we get going? All right. So that's one thing, do the student course evaluation. issue number 2, and I said this to some of you here earlier, the test that I had hoped to have ready on Wednesday, I had trouble getting into the system. See, they don't send us DVDs anymore with the test bank on them. They have us go online. So I tried to go online and nothing would cooperate. So I could not get the test done on Wednesday. Thursday was kind of most of my office hours were eaten up with L Day and other things like that. So I had no time in the office on Thursday. Friday I was over on the Birmingham campus, and my office there is in Dr. Pruitt's office. He wasn't in on Friday, so everyone who came to see him was directed toward me. And he didn't have a lot of traffic that day, but he always has some. And then I was working on the fall schedule, so I had 0 time to work on the test. I thought I'd have plenty of time this morning, and again, I had difficulty finding the link, but I did find the link finally and started working on the test, and then the phone started ringing, and I had people calling me and coming by, and so I got everything done except the last question. I just did not have time to type that. So it will be done shortly after class today, hopefully, knock on wood, as long as people don't keep coming by, and then I'll put it on Blackboard. So, and that you need to have in, if you can get it in Wednesday, that would be great, but if not, Monday. But Wednesday, I'll be giving you the test on Chapter 4, which we started last time, and we're going to get as far as we can today and Wednesday. And it'll be a fairly short test, probably 10 questions, but very straightforward, hopefully easy questions to do. And that would be the last exam. Technically your final exam, but it's just going to be another chapter test. All right. Any questions on anything we've done so far or what we still have to do? Okay. Now, we just had time to finish Theorem 4.1. Let's go back and review that. This was on Wednesday. Representation of antiderivatives. If capital F is an antiderivative of little f on some interval I, then capital G is an antiderivative on f on that interval I, if and only if capital G is of the form capital G of f is equal to capital F of x, capital G of x is equal to capital F of x plus c. And c can be any real number in the world, any constant. I guess it could be complex numbers. We're not really counting them as complex now. We're going to deal in the real number system for any constant. C cannot be a function of x. If it is, then this doesn't work. It's just any constant in the world. And that's true for all x's on that interval I. So in other words, if you find an antiderivative of a function, and you say, aha, here it is, then add c to it, and there's all of them. Okay? So that's the whole point of this, is that you can list all of them. Because there's more than one for any function, there's only one derivative. Okay? But for any function, there are an infinite number of antiderivatives because you can add any constant to the antiderivative. So, using Theorem 4.1, you can represent the entire family of antiderivatives of a function by adding a constant to a known antiderivative. So let's just do one. Knowing that, now I don't know if you remember this notation, this is derivative of the function with respect to the variable x. So this is the same as dy dx, okay, or whatever you want to call it, okay? The derivative with respect to x of x squared is what? 2x, okay? You can represent the family of all antiderivatives of f of x equal 2x. What would that be? Antiderivatives of 2x would, of course, be x squared plus c. You get this by taking derivative of that, but you see if this had been x squared plus 17 million, take the derivative of it, be 2x. Because 17 million, the derivative is 0. So, anytime you do an antiderivative, you have to put the plus c there, where c is any constant. The constant c is also called the constant of integration, okay? And that will take on really important consequences once you get to applying this to physics and probably engineering and things as well, okay? The constant of integration. A family of functions represented by g is then the general antiderivative of f, and g, capital G of x equals x squared plus c is the general solution to this differential equation, g prime of x is equal to 2x. Okay? So every time you take an antiderivative of a function, once you get the function that gives you this as its derivative, add a constant to it, plus c. A differential equation in x and y is an equation that involves x, y, and the derivatives of y. Okay? For instance, here's an equation. Y prime is equal to 3x. Where to stand? I'm in somebody's way just about always. And these are 2. Y prime is equal to x squared plus 1. These are examples of differential equations. Okay? And remember that y, the implicit understood thing is this y prime stands for dy dx. Okay? Is equal to 3x. And dy dx is equal to x squared plus t, plus 1. It wouldn't make any sense for this to be dy dt and this is x. That makes no sense. So be sure you understand that prime there means dy dx. D this variable over d that variable. Okay. All right. So find the general solution for this differential equation. And this time they wrote it right. They wrote it right. They wrote it right. Okay. dy dx is equal to 2. You tell me what you think y could be. Whoops, let me get my pen set up. Okay. Basically what we're going to do, if this is a derivative, we're going to do an antiderivative. So what function, when you take the derivative of it, do you get 2? Y is equal to 2x. Okay? Anything else? General solution, huh? Plus c. Make it general, plus c. C can be any constant in the world. Negative 14 pi over 3,015,000. You know, whatever constant that needs to be, it can take on that value. Okay? Does that make sense? All right. Good deal. Let me erase my scratch, and we'll see how they did it. They may have put in a few extra steps that you might find useful. To begin, you need to find the function whose derivative is 2. Well, y'all did that, okay? One such function is y is equal to 2x, exactly as you answered, but that's not the only one. You just need to add a constant to it. Now that you use theorem 4.1, since you have one function, add a constant to it, and you've got the general solution. Now, I don't know why they're using capital C's. Most books use little c. I don't know why. I will usually use little c, but I guess little c was used for critical values and they don't want you to get them confused. I don't know. But capital C is fine. There's nothing wrong with it, but I just typically don't use it. Okay. Now, here are a bunch of functions whose dy dx is equal to, when c is equal to 0, this is 2x. Okay? Slope of 2, y intercept is 0, 0. Okay? When c is minus 1, then its intercept is minus 1, then y-intercept is minus 1, and that still has a slope of 2. This has a slope of 2. That has a slope of 2. That has a slope of 2. This has a slope of 2. Yeah, all over the place, you have lines with slopes of 2. And that's exactly what dy dx is. It's saying, what function do you have a slope of 2? And every linear function, the slope is 2 is the answer. That, I mean, I can't think of any what he's saying. What the C's do is shift these, typically up and down. You don't see this. This is a +2 up here, a -1 down here. Okay. And here's, hold on. Find it. There you are. Okay. All right. Knee hurts. That's why it takes so long to stand up. When solving a differential equation of the form dy dx equals f of x, it is convenient to write it in the equivalent differential form. I was starting to do this, but most books don't do this until further along. So rather than write this as dy dx equals f of x, we write it in differential form that dy is equal to f of x dx, which looks an awful lot like you multiplied both sides of the equation by dx, which you didn't do, of course, because that's an operator, not a fraction. But it sure looks like it, doesn't it? Okay. Now, this operation of finding all solutions to this equation is called the antidifferentiation, or, now a new term here, indefinite integration, and is denoted by the integral sign. Basically, what we do when we integrate is put an integral here and an integral there. Okay? Now, I don't know if the book's going to do it this way, but this is typically how I do it and most people think of it. Okay? Now, when you do this, and you do these antiderivatives on both sides of the equation, only put 1 plus c. Because you can put a c on both sides, but then you can move it to the other side, and you only need 1. So, okay. So basically, what's the antiderivative of dy? Y. You got it. And this would then be what they've been calling your f of x, capital F of x, plus c. And that's it. Your antiderivative of whatever that function was. The previous time it was 2x. Okay? That would be x squared plus c. Or 2. That would be 2x plus c. Okay? Whatever the antiderivative is, that's what you get. So you see your antidifferentiation, that's exactly what you got. Y is equal to f of x plus c. Some antiderivative of that function, f of x. Okay? So antiderivatives, same as taking an indefinite integral. Later we're going to talk about definite integrals, but we'll get there. Okay? The general solution is denoted by, oh, here it is, exactly what I said. They didn't put the integral sign here. I find it's helpful to do that. That's where the y comes from. They just magically changed the dy to a y. Well, you integrated it too. They just didn't show it. You integrate this and you get the antiderivative of f of f, any antiderivative, and antiderivative of f of x, little f of x, is capital F of x, and then add a c to it, the constant of integration. The expression integral of f of x dx is read the antiderivative of f with respect to x, or the integral of f of x dx. You can read it either way. The differential dx serves to identify x as the variable of integration. The term indefinite integral is a synonym for antiderivative. Okay. Later we'll just talk about it as if they were integration. But, always I'll say, well, what's that antiderivative of f, little f? Yeah, and that's how you get this. Okay. Now let's see. That was example 1. Now, basic integration rules. The inverse nature. Now, let's take you back, maybe to kindergarten, grammar school anyway, when you first learned to add, right? I guess the first thing you learned to do was count, and then after a while they got you adding, right? And after learning all those addition tables and flashcards or whatever they use, and you thought, hey, I got this math down, then they turned it around and had you start subtracting, which was what? Undoing addition. Now, they didn't use this term, but it was an inverse operation for addition. So finally, when you got the subtraction done, and by the way, how did you check your subtraction? Add the bottom two, see if you got the top, okay? You use it because addition undoes subtraction, okay? They're inverse operations of each other. You say, okay, finally now we got this math underhand. But then they pulled out some multiplication. And you had to learn all the multiplication tables, right? And finally, when you got all those done, you said, okay, wow, almost through with this, except then they had you undo it with division, which undid is the inverse operation of multiplication, right? And how did you check division? Multiply. Either close it by the divisor, see if you get the dividend. If you had a remainder, then add that at the end. So, anyway, we got that done. Well, sometime way, way later, probably, you did things like raising things to a power, right? So, raising a number to a power of x squared, 5z cubed, or whatever, okay? How did you undo those? How do you undo a square? Square root. Undo a cube root. So you had inverse operations there. Okay, now, we've just done the first part of this course, differentiation, which is a whole new level of operation, a whole new math. And then what we're doing now is undoing that with this. The inverse nature of integration differentiation can be verified by substituting f prime of x, capital F prime of x for little f of x in the indefinite integration definition to obtain the integral of f prime of x dx is equal to f of x plus c. Okay? Remembering that integration undoes differentiation within a constant. Okay? Moreover, if the integral of f of x dx is equal to capital F of x plus c, then, so whereas integration undoes differentiation, differentiation undoes integration, okay? So if you take the derivative of an integral of f of x dx, the derivative undoes the integral, and you're left with f of x. Now, what's the difference? When you do the integral on the outside, differentiation's on the inside, integral, anytime you do an integral, you're going to have a plus c. This integral would have given you a plus c, but when you differentiate a constant, it goes away, so that leaves you just little f. So it's not exact, but it's pretty close, okay? The integration is almost exactly the inverse operation of differentiation, but when you integrate the derivative, you'll get the basic function, but then plus some constant. When you differentiate an integral, you just get the function that's inside. Okay? Because there's no differentiation constant, there is an integration constant. If you do that last, you're always going to get a constant. So, those two equations allow you to obtain integration formulas directly from your differentiation formula. You know how to differentiate, so let's see what we do. Basic differentiation formula. What's the derivative of a constant? 0. So if you integrate at 0, you get c, just a constant. Very good. What if you differentiate k times x? What do you get? Take a derivative of kx. What do you get? You said what you say? K, exactly. Okay. What happens if you integrate some constant k? Kx plus c. Don't forget your plus c. You always have to have the plus c when you do an indefinite integration. Okay, what if you have d by dx of, I love saying that, okay, k f of x. Yeah, it's helpful when there's numbers. But it's basically k times the derivative of f of x, right? The k is outside, it doesn't change anything, so it's k times f prime. Right? Well, what if you have the integral of, whoa, this doesn't go backwards. Yeah, okay. The integral of k times f of, I see what they're doing now, f of x. Now, this is not the same f of x as that is. That's the only thing that was throwing me here. Basically, when you integrate, pull the k outside too, and then integrate just the f of x. So just like you pulled the constant out of this when you take a derivative, pull the constant out when you're taking the integral. Unless you need the constant in there. If you do, use it. Like 2x, you need it for x squared. Okay? So, how about the derivative of the sum of two functions? What would that be? Sum or difference of two functions?
X plus or minus.
Yes, exactly. It's the sum or difference of the derivatives. Okay? Well, how about if you're integrating a function plus or minus another function? Guess what that would be? The integral of a sum or difference is the sum or difference of their integrals. So you just put them up and do them separately. Okay? Make life easier. Okay? This is our power function. What's the derivative of x to the nth power?
The nx minus nx to the n minus 1.
Exactly. You take the exponent, bring it in front, and then reduce the exponent by 1. What if you're integrating a power function? Think in reverse. Okay? Whereas before, you ultimately were going to raise that. You drop the x by a power of 1, right? Okay? This time you add. And before you multiply by the n, this time you divide by the n plus 1. So here it is. And you got to think backwards a little bit. And here we usually think of multiplying first and then reducing the power. When you're integrating, increase the power, because you got to do the reverse of it, and then divide by that increased power. So whereas here, you bring the n out front and drop the n by 1. Here you raise the n to n plus 1, and then divide by that n plus 1. But don't forget to put your c, okay? Always put the c. Now this does not work if n is equal to negative 1. Why?
You get a 0 at the bottom.
Yeah, you wind up with a 0 down here. So we're going to have to come up with a whole new function when n is equal to negative 1. We'll get there. If not in this class, in the next one. Okay, if you take Cal 2. That's your power rule. Basically, this is your constant rule, your linear multiplier rule, scalar multiplier rule, you might say, for x and for function, sum and difference rule, and your power rule. Okay? Ooh, more! What was the derivative of sine? Cosine. Guess what the integral of cosine is? Where'd you get negative? Sine x plus c. Don't forget your plus c. What's the derivative of cosine x? Negative sine. So guess what the integral of sine x is? Negative cosine plus c. Okay? Now, this is what drives people nuts. They just barely got this down, which one's positive and which is negative, and then you reverse them when you're doing the integration. So don't let it mess you. What's the derivative of tangent? Oh. Don't use it much, do you? Secant squared. So what's the integral of secant squared?
Tangent plus c.
Tangent plus c. Excellent. What's the derivative of secant x? It's a product.
Going way back.
Yeah. Secant x tangent x. So therefore, when you integrate secant x tangent x, it's going to be
C
plus secant x plus c. Derivative of cotangent x. It's going to be minus the secant, cosecant squared x. It's a lot like tangent x, only minus, whereas, get this, okay. You do the base functions, sine, tangent, secant, then those are always positive derivatives. When you do the cofunctions, cosine, cotangent, and cosecant, those are the three negatives. But then otherwise, they just reverse themselves just as you would expect. Derivative of sine is cosine, derivative of cosine would then be minus sine. Derivative of tangent is secant squared, so the derivative of cotangent would be minus cosecant squared. And derivative of secant would be secant tangent, so cosecant would be minus cosecant cotangent. So that would then produce over here derivative of cosecant squared x dx. The integral of that, integral of that would be
Cotangent x.
negative cotangent x. Plus c, don't forget the plus c, and because that's minus cosecant cotangent, the antiderivative of that, or the integral of that, would be negative cosecant x. Plus c, plus c.
So why does the negative not stay out front, like how the derivative of cosine is negative sine x? Why does it not stay out front on the integration? I mean, why is negative sine x dx not equal to?
Okay, all right, okay, wait, okay. All right, if this is what you're asking, if you're integrating minus sine x dx, that would come out cosine. Exactly.
Okay.
Is that what you're saying? Yeah.
I was just asking why we didn't keep the negative out front.
You could. I mean, it's fine. They just did it without it. But yeah, if you're doing either a minus here or a minus there, that would come up plus. Okay. And you don't need to change the sign of c because c is a constant. It doesn't matter what it is. The sign is. It's just a constant. Any constant, positive or negative, fraction or decimal, rational or irrational. I think we're keeping them real, but you know. All right. Those are your basic integration rules. So let's do example 2, since it rhymes every time. All right. Actually, at the bottom of the page, let's go back here. Remember this one that said this works as long as n is not -1. It works for all of it. It works for other negative n's. For any n, but it just can't be -1. So let's do that. What if n was -1? What if you're integrating n to the -1 dx? Okay? I'm sorry, x to the -1. N is equal to -1. Okay. Now, how's another way to write that? X to the -1 is?
X over 1.
No, 1 over x. Okay, 1 over x dx. All right. Now, at the bottom of this page, they say, note that the power rule, blah, 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 must wait until the introduction of natural logarithms in chapter 5. I don't have time to wait. Let's do them now, okay? This is the definition of the natural log of x. Natural log, and basically it has to be absolute value of x plus c because it's an indefinite integral. Also, that you always have to have the plus c. This is what natural log of x is. Now, if x is guaranteed to be positive, then you can just put log x. But you cannot take the natural log of 0, and you cannot take the natural log of a negative number, any negative number. And Chastity is here. All right. I'm getting a fairly good sized class. So there's something for the future reference. When that n is equal to -1, obviously can't use the power rule. That's where natural log comes into play. Which is going to turn around, and when you take the derivative of the natural log, guess what you're going to get? 1 over x. Or 1 over whatever the argument is. So this time we almost do the integration first and then come up with the derivative. Okay? All right. So let's now do, it says, here's example 2 describing antiderivatives. What is the antiderivative of 3x dx? They did the first step for you. They pulled out the 3. Okay? So you do the next step. I'll write down the 3. What's the antiderivative of x? What function, when you take the derivative of it, do you get an x? Okay. When you take the derivative, you're going to reduce the power, right? So you're taking an antiderivative, you increase the power. So what must be, and by how much? 1. So this is going to be, what's in the numerator? Increase the power by 1. Second? Second, 2x squared. But then you must divide by the 2. Okay? Plus c. Okay? So this would give you 3/2 x squared plus c. Whoa, get out of there. All right? Now, especially early on, when you're not used to doing antiderivatives and integration, I always suggest you take a derivative of your answer to see if you get what you started with. So if you take the derivative of 3/2 x squared, what would that be? 3x. Perfect. And that's what you had up here. Make sure when you take the derivative, you get what was in the integral to begin with. Okay? If you don't, go back and figure out what you did wrong. See, the plus c is just added to it. When you take the derivative of that, that's 0. So yeah, that's what you get. Now, that's my shorthand, and again, it's the reversal of the product rule. And how I suggest you reverse it, always raise it to the power and then divide by the power. Okay? That new power. Okay, so I'm going to erase my ink, and we'll see what they did. Well, they actually wrote a 1 in there. Isn't that clever? Okay? The 3 times the integral of x to the first dx. Okay? How do you take an antiderivative of the power, increase the power by 1, that will make it x squared, divide by that new power, x squared over 2. 3 times x squared over 2 plus c. Okay? And that would be 3/2 x squared plus c. And then my suggestion, especially while it's new to you, take a derivative and check. 3/2 times the derivative of x squared. Derivative of x squared is 2x. The 2 cancels out the 2 in the denominator. You're left with 3x. Derivative of c is 0. Perfect. That's what you had in the integral to begin with. The antiderivatives of 3x are of the form 3/2 x squared plus c, where c is any constant. You don't have to write out the answer every time, but just to get yourself with what you're doing. All right. Now, in example 2, note that the general pattern of integration is similar to that of differentiation. Okay? You start with the original integral. Rewrite it if necessary. Remember how we rewrote a lot of our functions before we took a derivative to make them easier to take a derivative. Then we integrate or anti-differentiate and then simplify if necessary. Okay? That doesn't add a lot to me, but they wanted to put it in there, so it's fine. Now, they skipped the next 5 examples. I think probably we need to do something, don't you? Just to get the things down. Rewriting before integrating. This is example 3. They have 3 in here. It says see larsoncalculus.com for an interactive version of this type of example. So let's do this one first. The integral of 1 over x cubed dx. Okay? What you reckon we're going to do first? Help me. So rewrite it. Good. And how would you rewrite it? Especially with Jeremy coming in. You need to rewrite it so you won't know what we're talking about. Okay. And also with Elijah coming in. My goodness, when it rains, it pours. Okay. As it did this weekend. Okay. All right. How would you rewrite this? The integral of x to the minus third dx. Okay? Now, that's a power rule, right? And what's the rule for a power? Okay. First thing you do is increase the power by 1. And minus 3 plus 1 is negative 2. And then divide by that new power. Right? This is undoing differentiation. Okay? So that's what we get so far. And that's going to have a plus c with it. And then you can simplify this a little bit. Negative 1 over 2x squared plus c. I'm not sure that's any simpler, but you've gotten rid of negative exponents, so that's certainly something to do. If I were integrating it, I would take this step and go back to this one, okay? Rewrite this as x to the minus 2. So negative 1/2 x to the minus 2. And take the derivative of that, negative 1/2 times the negative 1. Negative 2 times the negative 1/2 would be a positive 1, x to the minus 3, and that's exactly what we have. Okay? Do you see that? They first integrated it like we did. They rewrote it, integrated it, and simplified it. And that's what we got. All right? The B one they have, any questions on that one before we move on to B? Okay? The B one is the integral of the square root of x dx. What would be your first step? Rewrite it. And how would you rewrite it? The integral of x to the what? No, negative second would be 1 over x squared. This is x to the 1/2. I mean, this is square root of x. I just gave it away. X to the 1/2 power, okay, dx. Now, again, a radical indicates you have a denominator in your exponent. Whatever the index of the radical is, that's the denominator in the exponent. Whatever the exponent of the thing in that is, that would be your exponent up there. And this is the exponent of 1, and that's the 2. Okay, so that would be 1/2. So, what would be your anti-differentiation of it, or in other words, the integration of it? This is a power rule again. You can have fractional powers. What would that be? 3 over 2 times, or divided by, or whatever. 3 over 2. Now I'm going to give you a hint here. And this is a simplification, I guess. That would be the same as x to the 3/2 divided by 3/2 is the same as times 2/3, right? Because you're dividing by a fraction, you invert and multiply, right? So this would be 2/3 x to the 3/2. What have I forgot? Plus c, excellent. Okay. Now that plus c is down there on the same line with the x, not up there with the 3/2. I realize my writing was sort of slow. I really should have done that on the previous slide too. I just didn't have things right here. Let me correct that just so your notes won't indicate something wrong. Okay. It's that entity plus c. Okay? Guess what you do to check it? 3/2 times 2/3 is obviously 1. X to the, subtract 1 from this, subtract 2/2 from 3/2, you get 1/2. That's exactly what you got up there. Right? And the derivative of c is 0. All right. Think we can fit c on the bottom, or should erase this? Let's erase it just in case. Okay. 3c, the integral of 2 sine x dx. Okay, get out of there. Okay. There really isn't too much to rewrite here, but probably a little bit. What would you do? Yeah, move the 2 outside. 2 times the integral of sine x dx. And what is, that would be 2 times, what's the antiderivative of sine x? Negative cosine x, yes, don't forget. Okay, well, what else? Plus c. Okay, so this will be a minus 2 cosine x plus c. Okay? Yeah, that's my nose is itching. I must be going to have company. All right. And if you were going to check this to see if you got it right, take the derivative of cosine and you get derivative of cosine is minus sine. So that takes care of the minus, so it becomes a plus 2 times sine x, and that's what you have. Derivative of c is 0. All right, those were the 3 on example 3. And again, LarsonCalculus.com has interactive versions of others like this. Okay? So we're going to move to example 4, and I think I'll erase this one. So we'll start fresh here. It has 3 parts as well. And the first one is something pretty easy. Integral of dx would be what? How would you rewrite that? Huh? It's just x. Well, what else? Plus c. Okay, very good. That's it. They put a 1 in there. I don't see any reason to do that. It's x plus c. That was pretty easy. How about this one? The integral of x plus 2 dx. Now, I don't know if it's necessary to do, but maybe when you're first getting started, it's not a bad idea to do. How could you rewrite this? I'll start with an integral sign. Wouldn't that be the same as integral of x dx plus 2 times the integral of dx? Or you could write it plus 2 dx and then pull the 2 out. But isn't that, remember your sum and differences? You just integrate each part, right? Okay, what's the antiderivative of x? That's the power function, right? What's the x to the power up here in the integral? What's the power of that? 1, okay? So you increase that by 1 and you get x squared divided by 2. Don't do a separate plus c. Wait till the end and do 1 plus c. Plus 2, the understood coefficient there is 1, 2x. That's it. Plus c. Got it. So there you have it. There's your answer. You could rewrite it if you wanted to. I don't know why, but you could. As 1/2 x squared plus 2x plus c. Okay? How do they? Yeah, they leave the x squared over 2. I like it that way too. Okay? Let's do, they wrote in both plus c's. I just said, wait and just do 1c at the end. Because c1 plus c2 is still some constant c. Okay? Let's do the third one. Okay. The integral of 3x to the 4th minus 5x squared plus x dx. Okay? Now they want you to rewrite it first. Oh, they don't either. Look at them. Okay? They don't have you rewrite. They don't have you do anything. They're moving you right along here, folks. Okay? And here's what they're doing. They're doing all this mentally, I guess, because they're skipping all this steps. Let's just first integrate this. And what would the integral of that be? The antiderivative of x. 3x to the 4th. Well, the 3 is going to be in front, so let's get that there. And what's the integral of x to the 4th? x to the fifth over 5. Done. Let's move to the next one and pull out a minus 5. What's the integral of x squared? X cubed over 3. And what's the integral of x? X squared over 2 plus c. Done! Isn't that easy? Okay? Now, I think they go back and rewrite it, but they don't need to. 3/5 x to the fifth minus 5/3 x cubed plus 1/2 x squared plus c. Now, I say it's not necessary. Only thing that you might find it useful for is when you're checking. Because when you check this, 5 times 3/5 is 3x to the fourth. Can you go? Oh, I gotta say that in all that. Minus 5/3 x cubed. 3, if you're taking the derivative of that, 3 times 5/3 would be 5 minus 5x squared. Yeah. And then this would be 2 times 1/2 is 1x. There it is. Derivative of c is 0. All right. Does that make sense? And see, integrating polynomials, pretty easy. Take as many steps as you need. If you don't see this written as 1, write it out. You know, the integral of, or 3 times the integral of x to the fourth minus 5 times the integral of x squared plus integral of x dx. You know, have a dx with each one of them. Take as many steps as you need till you get used to it, and then once you don't need it anymore, skip them, you know, if you need to. So there's example 4. Let's do example 5. Again, they don't do this one. Okay. They jump right in here, don't they? Integral of x plus 1 over the square root of x dx. That almost looks like something you should do in a later chapter, okay? That's a pretty tough looking integral, isn't it? No, not really. How would your first rewrite be, do you think? I'm going to really stretch this out way many steps. This will be the same as the integral of x over the square root of x plus 1 over the square root of x dx. Do you buy that? Was that correct? All you're doing is splitting a monomial denominator, sum up here, so that's the same as this over this, plus that over that. It's just the reverse of what you do when you're adding fractions. Once you have the common denominator, add the numerator, keep the denominator. So this time we're keeping the denominator and separating the numerators, right? So you buy that, it's okay? Yay? Nay? Okay. Next thing I'm going to do, you don't have to stretch it out like this, but it's okay to, if you need to. This will be the integral of x over square root of x dx plus the integral of 1 over the square root of x dx, right? That's your sum, you know, sum or difference rule, right? You just, the integral of a sum or a difference is the sum or difference of the integrals, okay? Now, again, this is way too many steps. I'm going to rewrite this one as x to the first, we don't usually write that, do we, over x to the 1/2. Perfect. That'd be dx plus, let's just rewrite this as integral of x to the, say again? Huh? Nope, not 0. Negative 1/2. You brought it upstairs, so you have to change the sign, right? I could have done that before, but I thought maybe for what I was going to do next, which is this. Okay, that's the integral of, what do you do if you're dividing same base, different exponents? Keep the base, x, and subtract the exponents. 1 minus 1/2 is 1/2. Exactly. Dx plus the integral of x to the minus 1/2 dx. Okay? Let's do that first one. what would that be? We're integrating. X to the, this is a power rule. Say again? You said 3/2? Yes, 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 3/2. But if you do that, you also have to put divided by 3/2, which is the same as multiplying by 2/3. Whoop, 2/3. I can't write. Okay. Okay. All right, there's that one. And don't do an extra plus C here. Wait till the end. Plus, what would this one be? X to the 1/2 times 2. Now you can do your plus C. So this will be 2/3 x to the 3/2 plus 2 x to the 1/2 plus c. And if you wanted to go back and make them radicals, you could do that too. I don't see any reason to. Do they do it in the book? Yeah, they do. Yuck. Okay. Well, they do all sorts of weird things to it. Wait a minute. Yeah, I got it. 2/3 x to the 3/2 plus 2x to the 1/2 plus c. All right. Now they do something else here. Okay. I could not find you in here. Okay. All right. Here's what they do. And there's really no reason for it, but you can do it. 2/3 and x to the 3/2 is the same as x times x to the 1/2. Would you buy that? Okay. Plus 2 times x to the 1/2, right? Plus c. Well, there's a common factor there, right? X to the 1/2. Okay? So pull out an x to the 1/2 power. Now they actually pull out, we'll come back and do the next part later. And that would leave us 2/3 x plus 2 plus c. Okay? But for some reason, they decided they didn't like that 2/3. So they're going to pull that out as well. Okay? So it'll be 2/3 x to the 1/2 times, and what you have left when, did they pull out 2/3 or 1/3? No, they pulled out 2/3. Okay. Strange. I would never have done this. That just left them an x here plus, now, here's the weird part. Dividing, factoring out of 2/3 is the same as dividing. Dividing 2/3 by 2/3 is 1. So that's where you get that coefficient. Dividing 2 by 2/3 is the same as multiplying by 3/2, which you get make this a plus. Okay? Why in the world they did this, I do not know. Okay? Plus c. That's another expression of this. Well, and then finally what they did is 2/3 the square root of x times x plus 3 plus c. Now, never in a million years would I have said, oh, you need to do this for your answer. But if you're doing WebAssign with this, and for some reason they decided that's the answer they wanted, I probably would have kept guessing answers. I mean, not guessing, I mean coming up with new expressions. I'm not sure I would have ever settled on this one. And probably run out of trying to do, actually would definitely run out of frustration. Yeah, I mean, gotten totally frustrated at it because it would have kept telling me the wrong answers. I knew that answer was right. Any of those answers were right, but they're only looking for one. So that's one reason I don't use WebAssign. Sorry, folks. I know y'all love it and want to use it. Guess what? Not me. Okay. Bizarre way to write an answer. Okay? And they put a little thing in here that should be in the PowerPoint, but it's not. When you're integrating a sum or a difference, you can split those into the sum or the difference of the integrals, right? That's okay. Don't ever do that with products and quotients. Ever. Remember, you have a whole new product rule for derivatives and a quotient rule for quotients. You can't just automatically, oh, well, that's just the, don't even be tempted. I wish I hadn't put it here, because it may plant the idea in your head you can. Don't, okay? But they did do a thing here, okay? Let's move on to example 6. Boy, they do the very simplest ones and then leave you to puzzle with the ones they don't show. Example 6, how about, ooh, my goodness, this one. The integral of sine x over cosine squared x dx. This is really incredible that this early in the game they're giving you this complicated of a problem. Okay? Now, later we'll learn some techniques for doing this. But this one you can do without any of those advanced techniques. But you got to be fairly clever in figuring out how to rewrite this one. Any ideas? Say again? Okay. Here's what. You could rewrite this way. Sine x over cosine x times 1 over cosine x. Would you buy that's true? Yeah, that's just splitting the denominator, right? Now you tell me what sine x over cosine x is. That's tangent x. And what's 1 over cosine x? What again? Secant x. Right? Dx. Now, does anything come to mind? That's the antiderivative of secant x. Second? There's something else. There's something else. Plus c. Okay, good. Okay, now, remember, derivative of secant x is secant x tangent x. Usually we write them in the other order. Okay? So that's why integral antiderivative of secant x tangent x is just simply secant x. Right? Now, again, knowing what I know, I would approach this very differently. But this is indeed true. Let me make sure they did. Yeah, secant x plus c. They got it right. Woo, example 7. 4 sub-examples, okay? So let's clear the screen and get ready for those, or at least 1 or 2 of them, before we clear the screen again, okay? The antiderivative or integral of 2 over square root of x dx. What would you do first? As? How about, yeah, I would just put the 2 out front. 2 times the integral of x to the negative 1/2. Is that what you said? Dx. Okay. I don't know if that was a wise move or not, but it's okay to do. Pull the constant out. Okay? Now, that gives you 2 And the antiderivative of a product, a power rule is what?
Add 1 and divide by your new.
Right? And that would be x to the 1/2 over 1/2, which is the same as multiplying by 2 plus c. So this will be 4x to the 1/2 plus c. And if you wanted to go back and write it as a radical, that would be 4 times the square root of x plus c. Now, I don't particularly like the radical form ever, so I would have left it like that. But since your problem started with a radical, you might want to write it as that. But in order to check it, I have to write it in this form, right? So to check this, we do 1/2 times 4, 2 x to the minus 1/2, 2 x to the minus 1/2. Yeah. So that does check. Okay. Any question on that? 4x to the 1/2. And they left it. They didn't go back and put a radical. They did on that 2 examples ago, and I could not figure out why, but they did it. Okay, let's do the b here. This is the integral of t squared plus 1 squared dt. All right. Now, there are some other ways to do this problem that we'll get to in a future course. But in this course, there's really only one way to proceed here. And what would that be? Second? Okay, yeah, you could FOIL it or use the squaring binomial square rule. So however you do it, what you get the integral to be? Anybody? T to the 4th plus 2t squared plus 1 dt. Okay? Now, what would you do with that? Yeah, you could break it into 3 integrals added together, the sum of 3 integrals, but if you can do it just like this, do it. What's the integral of t to the 4th? T to the 5th over 5 plus 2 times t to the 3rd over 3 plus t plus c. Excellent. Okay. So you could rewrite this if you wanted to. It seems like the book does. 1/5 t5 plus 2/3 t cubed plus t plus c. That's a pretty ugly t. Let's see if that's how they did it. 1/5 t5 plus 2/3 t cubed plus t plus c. Fantastic. Any questions on that? You see how we did it, why we did it, what allowed us to do it. Okay? Let's move on to the C one. Example 7c. The integral of x cubed plus 3 over x squared dx. What would be the first thing you would do on this one? Rewrite? How would you rewrite it?
X cubed plus x to the negative 2 plus 3.
Ooh, let's not. Let's split the fraction. Over x squared plus 3 over x squared dx. Okay, how would you rewrite the first of those? What's x cubed divided by x squared? X, right? I'm going to write that as a dx plus 3 times the integral of, how would you write 1 over x squared? x to the minus 2 dx. Okay? Now what would that first one be? X squared over 2 plus 3 times. Okay, it's going to be x to the what? Negative what? I can't hear her well. Ah, I thought that's what you said. Okay, over. Over a negative 1, which is just basically all it's going to do is change your sign. So I'm going to be real sneaky here and just change the sign there. Right? You okay with that? All right, good. And then finally, plus c. Don't forget your plus c. Okay? And if we wanted to, you could rewrite that a little bit. 1/2 x squared minus, and then you can move this downstairs, 3 over x plus c. That's no better than the previous, but you could. But if I was going to check it, which I usually do because I don't like making mistakes, and I like even less for you to make mistakes, because when you make mistakes, I have to figure out why you made your mistake, and it's harder to grade. I like to just put a bunch of check marks. So don't make mistakes, okay? Check your answers, okay? Let's do this one. 2 times 1/2 is 1, so that'd be x. And sure enough, we got an x there, okay? It's going to be hard to go back and do this without doing it, so let's just do, that would be an x. This would be a minus 1 times a minus 3 would be positive 3 x to the minus 1. I mean, x to the minus 2. And that's exactly what we've got there, plus 0, okay? And then you can go backwards from there to get back to here. So, yeah. I'm confident that's right. Let's see what they got. 1/2 x squared minus 3 over x plus c. Look at that. They got it right. I think I'm going to erase that one. Anyone need this up there a little longer? Okay. So let's do the D one. This is the integral of the cube root of x times x minus 4 dx. What in the world would you do with that? Rewrite. How would you rewrite it? Okay, x to the 1/3 times x minus 4 dx. Now, what could you do next? Distribute. Integral of x to the 4/3. That was very good. Okay, because x to the 1/3 times x to the 3/3. Keep the base, x, add the x one, it's 1/3 plus 3/3 is 4/3, fine, minus 4 times x to the 1/3. And then you write your dx, okay? Now you could split this into two integrals, the difference of two integrals, or you could just integrate it in place and see what you get. What would that be? X to the, how many? I can't hear you. You may have said it right, I just can't hear well. He's doubting himself because I did this to him last time. You may have said it right. I'm on my 7/3. Is that what you said? Yeah, okay. I just couldn't hear. 7/3. Okay. But then you have something else. Second? Yes, times 3/7. Right. Is that what you were saying? I thought so. Okay. All right. All right. Next. Minus. I'm going to put the 4 out there. X to the 4/3 over, or times, or whatever, 3/4. Well, the 4 is going out, and that's just going to be 3, right? Now, I sort of did a sleight of hand there. Are you okay with that? I had a 4 out there. I multiplied by 3/4, and that just left me with a -3. And then what? Yeah, the 4's canceled. And then what else? Plus C. Don't forget the plus C. So let's clean this up a little bit. 3/7, and the book likes it this way. I don't see any reason for it, but it's okay if the book likes it. Yeah, that's fine. X to the 7/3 minus 3, x to the 4/3 plus C. Okay? Now, if you wanted to go back and put that where radicals knock yourself out, I don't see any reason to. Let's just check this and see if we take a derivative of this. It would be 7/3 times 3/7 would be 1 x to the 4/3. And sure enough, it gives you x to the 4/3. And here, that would be minus 4/3 times 3 would be minus 4 x to the 1/3. Sure enough, that's what you got. And then back up from there and see if you get back here. You will. Okay? Let's see how they leave it. I think they wrote it the same way. 3/7 x to the 7/3 minus 3x to the 4/3 plus C. And it says here at the bottom, as you do the exercises, let me say that again. As you do the exercises, okay? All right, hint, hint. Note that you can check your answer to an anti-differentiation problem by differentiating, which I've tried to do just about every time, for instance, in blah, blah. So we've already done that. They did example 7a, and we had already done that. All right, so we're through with that. Let's move on to initial conditions and particular solutions. Okay? Now, you've already seen that the equation, sorry, I hurt my knee over the weekend. It's so hard to stand up from being in one position for very long. It's better after I work it out. Okay, you've already seen that this equation, y is equal to the integral of f of x dx, has an infinite number of solutions, okay? Each differing by a constant. Whatever that antiderivative is of f of x, and you get that, you add any constant you want to it. An infinite number of constants. This means that the graphs of any two antiderivatives of f are vertical translations of each other. If you have one like this, you have one just like it like this. I mean, they just go like we saw before. They drew them as if they're horizontal, but they're actually more vertical, like here. For instance, the example for figure 4.2, that one, shows that the graphs of several antiderivatives of this form. Y is equal to the integral of 3x squared minus 1. What would be that integral? Over 3, which would be
3 over 3 is
1. So that would be x cubed minus x. Okay, that would be x cubed minus x plus c. Okay. Now, if the c was 0, x cubed minus x would be this one right here. C is 1. It just translates up here. C is 2. C is 3. C is 4. C is 5. C is 1/2. C is 3. There's an infinite number of those. And C is minus 1 is down here. Minus 2, minus 3, minus 4, minus 2.5, minus 1 1/3. Whatever. You just get more and more. They're all parallel to it. They don't look parallel, but they really are, the same function, just vertical translations. Okay? Each of those antiderivatives is a solution of this differential equation. As you see, we got this by, we didn't multiply, but make it dy is equal to this thing dx, and then integrating both sides like that. Okay. So, every one of those is a antiderivative of this. Well, what if your differential equation, you knew one tiny little point that was on your real solution? Okay? Well, if you did that, then you just plug in. If you knew what the x was, plug that in, you knew what the y was at that x, you can evaluate to see what the c would have to be to make that your solution. That's what we're going to do now. It's called initial conditions and particular solutions. In many applications of integration, you're given enough information to determine one particular solution, not an infinite number of them with a plus c, but one. To do this, you only need to know the value of f. Y is equal to f of x, that's your capital F, for one value of x. Okay? And that's called an initial condition. Now, it's true. I mean, that's what the books call them now. Back when I first learned these kinds of things, I understood that to be when t is equal to 0, when you have functions of time. That would be your initial condition. But what it means, you just know one value, let that be your initial condition. For example, in figure 4.2, that one we saw there, only one curve passes through the point 2, 4. Okay? Now, we get to go back and look at it, but to do it, you use the general solution. This is your capital F of x is equal to x cubed minus x plus c. That was right, wasn't it? I was thinking it was a plus x, but it was minus. Yeah. Okay. Yeah, it was minus. Okay. Okay. Now, if you know one point on it, that 2, 4 is on that graph, that means that f of 2 is equal to 2 cubed minus 2 plus c, but that's equal to 4, right? Well, 2 cubed is 8 minus 2 plus c has the equal 4. 8 minus 2 is 6 plus c is equal to, that's 4. I don't know where the 0 came from. Get that out of there so that people don't get confused later. And what would c have to be? C would be, subtract 6 from both sides, and you get c is equal to negative 2. Now you go back and say your answer, f of x, is equal to x cubed minus x minus 2. There's your answer, the one and only function that you really are interested in, because you wanted it to have that point on the function. Well, let's go back and see if we can see that. I'm about to drag my computer off the table, which is not a good thing. The point 2, 4, wasn't it? There it is, way up there. 2, 4. Got it? We'll follow that line down here, and sure enough, that's the one that c was equal to negative 2. And that's exactly what we got. Right? Okay. Good deal. It's called an initial condition. Okay? By using the initial condition here, they do the same thing we just did. In the general solution, you can determine f of 2 is equal to 8 minus 2 plus c, and that's got to equal 4, because that's what we took. F of 2 is equal to 4. That means that c, capital C, is negative 2, and then your particular solution is f of x is equal to x cubed minus x minus 2. That's the one that works for that initial condition and all the others you're interested in. All right. Do we have time to do this one? I kind of guess not. Okay, so let's pick up and go from that. Whoa, well, I'll use this. Okay. Next time. And let's give you, we came close to finishing. Homework exercises, due number 5 is at calcchat.com. Do either 7 or 9. They're both at CalcChat. 7's at CalcView. Do either 11 or 13 or both. 11's at CalcChat. They're both at CalcChat. 13's at CalcView. Do any of the odds 15 to 35. They're all at CalcChat. 15's at CalcView. And I think you can probably right now do any of the odds 37 to 43. They're all at CalcChat, but 37's at CalcView. If you don't feel comfortable doing it, since we sort of talked about it but didn't do an example, you don't have to do those until next time if you want to hold off on those. And then the rest of that we'll pick up later. Any questions? Okay. Now, for those who came in late, let me say this. And for those who were here before, I'll say it again. Sorry that I didn't get your test finished. I got your test, the questions picked out, but I had to retype them into a program because the format they come across is just really wacko. So I was in the process of doing that. I got interrupted so many times. Got one more to do. So what I'm going to do, I'm going to put your Chapter 3 test on Blackboard. So it'll be there as an attachment in Blackboard. Look under, well, you'll get an email with it in it too, because I'll have them send it as an email message as well. So it'll be under, what will it be? Announcement, no. Content, it'll be under content. And I'll make the announcement. It'll be somewhere in there, but it'll be in an email. I'll have it. I think. I don't know how they do it. Okay.
You turned it on? I got it early.
Good deal. All right. Wow. And it rains reports. Good deal.
It usually goes on the content.
Yeah, I think it is. I think that's what it is. But since I'm going to be, I'll make an announcement, and when I make an announcement, well, let's see. I don't know if I can put an attachment on an announcement. I'll figure out some way, but yeah, I think it's on, yeah.